Hello and welcome to our lecture on Trellis coded modulation. Let us start with the brief outline for today's talk. We would introduce this interesting notion of combining coding and modulation. So, we will look at combined coding and modulation. Then we will move on to the idea of Trellis coded modulation. We will then characterize the free distance and come up with interesting idea proposed by Ungerboek in terms of his design rules. Of course, we will look at some examples as we go along. So far what have we done? We have looked at block codes, linear block codes, we have looked at cyclic codes, BCH codes, then we changed gears and looked at codes with memory, and we looked at convolutional codes and turbo codes. And now we move on to a completely different area where we look at coding and modulation combined together. But why do we do that? So, first let us look at the trade off between bandwidth and performance. We know that in all error control coding techniques, extra bits are added to the information bits in a known manner, therefore, the receiver can decode it. But this is not free. Additional bits come at the expense of additional bandwidth, and as we know, bandwidth is not cheap. The bandwidth expansion is equal to the reciprocal of the code rate. For example, if you have the Reed-Solomon 255,223 code, then there is a 1 over r equal to 1.14. So, there is a 14% expansion. Now, this tantamounts to, for every 100 information bits, we have about 14.35 overhead bits on an average. So, a 14.35% expansion of bandwidth. This is non-trivial even for an efficient code like Reed-Solomon 255,223. So, in power limited channel, one may trade the bandwidth expansion for the desired performance, but for bandwidth limited channels we may not have this luxury. So, can we do better? For example, telephone lines are bandwidth limited, and if we want to push data over telephone lines, we need to work more smartly. So, let us look at coding and modulation. How can we talk about coding and modulation on the same slide? Well, traditionally coding and modulations have been considered as two separate parts of our digital communication system. You first do coding and then follow it up by modulation, right. First the input stream is channel coded and then we convert into an analog waveform by the modulator. But if you look at it more carefully, the objective of both the channel encoder and the modulation is to correct errors, and this is because of the imperfections in the channel. So, both of them are doing the same job. If you look at an error control code, we find out what is the probability of residual error. If you look at the characteristic of a modulator, we always plot the BER versus the SNR curve, the standard waterfall curve. So, again we are talking about bit error rate. So, now both these blocks are optimized independently, even though it seems their objective is the same. Now, a higher performance is possible by lowering the code rate at the cost of the bandwidth expansion and increased decoding complexity. That is what we have learned so far. So, if you need a stronger code, you have to have a poorer code rate, because that is how you will be able to recover from more number of errors. Now, the question is it possible to obtain this coding gain without the bandwidth expansion? Is there a free lunch? Can we get something out of nothing? That is the question we are asking, whether both coding and modulation can be looked at together to give you this gain without additional bandwidth requirement. So, let us understand this with a simple example. Suppose we are looking at data transmission over a channel of throughput 2 bits per second per hertz. Okay. So, the moment I see 2 bits per second per hertz, my mind jumps to uncoded QPSK, where we have 2 bits per symbol. But we say, wait a minute, we can do this differently. We first use a 2 by 3 rate convolution encoder, and it takes the 2 bits of raw data and converts it into 3 bits of coded data, and then 3 bits have to be transported, and we use now an 8 PSK, because I need 3 bits per symbol, because I do not need additional bandwidth. So, this coded 8 PSK schemes yield the same information data throughput as the uncoded QPSK, which was sending 2 bits per second per hertz. We assume that QPSK and 8 PSK are consuming roughly the same bandwidth. It is not a bad assumption. But we know that the symbol error rate for 8 PSK is worse off than that of QPSK for the same energy per symbol. But on the other hand, the 2 by 3 convolution encoder has been able to provide some coding gain. So, if you look at it graphically, this is what we did. We had this 2 bits coming in. Now, if you look at this 2 bits, this 2 bits can be either sent using QPSK, okay, where you know there is a constellation diagram, and we have these 4 possible symbols in the constellation diagram, and you have got 2 bits per symbol. But we say no, wait a minute, these 2 bits can be passed through a convolutional encoder, which is rate 2 by 3. So, 2 bits go in and 3 bits come out. But what do? I have to modulate and send. So, I need a higher order modulation scheme. So, I need probably an 8 PSK. So, if you look at it, this is my 8 PSK, this is the constellation diagram. Here I have got 3 bits per symbol. Please note that this radius of the circle is proportional to the energy per symbol. So, we do not want additional power. So, the radii are the same. So, the same radii implies that this circle has these symbols closer together as opposed to the distance. So, the Euclidean distance goes down. So, the Euclidean distance going down may lead to an increase in probability of error, but you already have an error control code put into place, whose job is to reduce the error. So, this block is going to reduce the probability of error. So, on one side we have a mechanism that tries to push down the error, the other side may lead to increase of error. So, if you play our cards right, then we can come out an overall winner. So, this trade off will decide whether we finally end up having a better BER. Please note, we have not touched power. So, same power. And here these two modulation schemes, we have not really asked for additional bandwidth. So, we have same bandwidth. Now, with the same power and same bandwidth, do we have an improved BER? That is the question. Did we really gain something out of nothing? We know that from Shannon's theorem, you give me more power, I will give you improved BER. you give me more bandwidth, I will give you an improved BR, but I ask for no additional power, no additional bandwidth, and am I going to get an improved BER? So, the answer is yes, and let us see how we can do it. So, we go back to our slide, and what we have just mentioned, it could be possible that the coding gain provided by the encoder outweighs the performance loss because of the 8 PSK signal set, as we are looking in our slides. Now, if the coded modulation scheme performs superior to the uncoded one at the same SNR, we can claim that an improvement is achieved without sacrificing either data rate or bandwidth. So, please note, we did not sacrifice data rate in either case. We got those 2 bits per second through the channel. So, in this example, we have combined a Trellis encoder with a modulator, and hence we have looked at combined coding and modulation. This scheme is called a Trellis coded modulation, or TCM for short. So, let us look at QPSK and 8 PSK a little bit more carefully. If you see that both the circles are of the same radius, which means that energy per symbol is the same. Now, we also know that the probability of error depends on the Euclidean distance. Here, the smallest Euclidean distance between S1 and S0 will decide what is the error rate. So, I have put delta 0 as the first distance. If the radius of the circle is under root ES, then the distance between S1 and S0 delta naught square would be 2 ES, and similarly the second possible distance between S2 and S0 will be 4 ES. On the other hand, if you look at 8 PSK, the distances are shorter. So, the smallest distance possible delta naught 0 is 0.586 ES, where ES represents the energy per symbol and the radius of the circle is under root E of S. Here delta 1 squared is between S0 and S2, same as delta 0 squared in QPSK, but we have 2 other distances delta 2 and delta 3 listed here. So, this smaller distance leads to a higher error for 8 PSK. So, we make some observations. We observe that the expansion of the signal set in order to provide redundancy results in the shrinking of the Euclidean distance. This leads to an increase in the error rate, which must be compensated with the coding gain, that is the increase in the Hamming distance. We also note that the use of hard decision demodulation prior to decoding in a coded scheme causes an irreversible loss of information. So, these are the observations we make. And finally, this hard decision decoding leads to loss of SNR. Some more observations. So, for coded modulation schemes where the expansion of the signal set implies power penalty, use of soft decision decoding is imperative. Okay. As a result, demodulation and decoding should be combined. So, not only the modulation and coding is combined, the demodulation and decoding itself is combined at the receiver side. For the maximum likelihood decoding using soft decision, the optimal decoder chooses that sequence which is nearest to the received sequence, this time in terms of the Euclidean distance and not the Hamming distance that we saw in the last time. So, what is an efficient coding scheme? It should be based on maximizing the minimum Euclidean distance between coded sequence rather than the Hamming distance. We have looked at free distance earlier in terms of convolutional codes. We define the free Euclidean distance. So, the minimum Euclidean distance between any 2 paths in the trellis is called the free Euclidean distance d free of the TCM scheme. Please note here, since there is a convolution encoder present, there will be a trellis diagram, but the labels of the branches instead of being bits should be symbols, because all the bits have been mapped to symbols. Now, you must remember, in convolutional codes we had the linearity constraint. So, we were working with linear codes. We could take the all 0 path and find out the d free with respect to the all 0 path. Here is a word of caution for TCM. TCM is nonlinear. Therefore, in order to find the d free, one must look at all possible pairs within the trellis diagram. Okay? We are looking at nonlinear codes. This mapping of the bits to the symbols introduces the nonlinearity. So, let us look at the decoding. Please note there is a Viterbi algorithm associated with it, simply because we have a trellis diagram which is used for encoding. So, we do the decoding using the Viterbi algorithm, which we have studied already in the context of convolutional codes. What does the Viterbi decoding do? It looks for the most likely path through the trellis, but this time instead of finding out the most likely path closest to the received sequence in terms of Hamming distance, we should be using the Euclidean distance for TCM. The performance of the decoding algorithm depends on the minimum Euclidean distance between the pairs of paths forming an error event. What is an error event? First, the paths diverge and then they merge back. Okay. So, we come back to our slide. We have done all of So, let us look at this example now. Let us consider a simple example where if you see a trellis encoder in the beginning, it takes in 2 bits A1 and A2 and gives out 3 coded bits C1, C2, C3. But the moment I get these 3 bits, I use a natural mapping on 8 PSK and it gives me a symbol. So, if you look at the combined coding and modulation, 2 bits lead to 1 symbol. What is natural mapping? It is 000 is S0, 001 bit means transmit S1, these are the symbols. 010 transmit S2 up to 111 means transmit S7 symbol from the constellation diagram. The rate is clearly 2 by 3 and it takes in 2 bits and converts it into 3 bits and the constellation is 8 PSK. So, if you see that this combined encoding and modulation can be represented using a trellis diagram, but this time we label the branches with the output symbols. And this is a fully connected trellis where each branch is labeled by the symbols from 8 PSK. And encoding is a simple process, as we had learnt earlier. 1 comes in, you take the upper branch, 0 comes in, take the lower branch, and you read out what is written on top of the branch. So, if you have to look at the trellis diagram, you just take in the input bit stream which tells you which path in the trellis you have to take. Let us take a simple example of a sequence of bits to be encoded using the trellis coded modulation scheme. Say the bit stream is 101100001001. This has to be encoded using the trellis coded modulation scheme. So, here is the corresponding trellis for the TCM schemes. Now, please note that instead of labeling each branch and it becomes a little confusing, we write the symbols here. So, S0 corresponds to the first branch label, S7 corresponds to the second branch, S5 third and S2 fourth. So, let us look at it graphically here. So, we draw this trellis diagram. There are 4 states in the trellis, because if you see, you have 2 memory units leading to 4 states, and it is a fully connected trellis, which means that each node is connected to every other node. and so on and so forth. Now, for any bit that comes in, and this is a rate 2 by 3. So, 2 bits come out. So, there are possible 4 possible transitions. Okay, 0 0 comes in, take this branch, 0 1 take this one, 1 0 take this branch, 1 1 take the last branch. What happens? Once you take the branch, you get an output bit, but you encode it using, and then you map it back using the 8PSK natural mapping. So, the mapping strategy that we have given is S0 for 1. What is this S0? Well, if you look at your 8PSK, these are your symbols. So, this is your S0, this is your S1. So, this S0 is this S0. But suppose you go for this transition, then you label it with S7. This is a design that we have come up with. I could have labeled it something else, but we are not yet looking at the design criteria. And then the third branch is S5, the fourth branch is S2. If I start labeling all of them, it gets a little congested. So, we can say this is S0, S7, S5 and S2. So, this is the convention. Similarly, for the next one I can write S5, S2, S0, S7. Of course, it will be easy to start connecting them and labeling and so on and so forth. And similarly, the third one and the fourth one, and this repeats. So, we just fix it and write out the trellis S4, S6, S1, similarly S6, S1, S3 and S4. Right. So, we can always write a trellis diagram in a compact form. So, let us look at the slides again, and if you see this fully connected trellis, then we must now find out a way to encode the path in the trellis. So, it says the bits input bit stream is 1 0, 1 1, 1 0 and 0 0 in the slide. So, what we do is look at the first 2 bits. Since encoder and decoder are friends, we know that 2 bits are encoded at one time, and the encoder then takes 1 0 means takes the third path, then 1 1 take this path, and then so this basically gives which is the direction to take, which sequence of bits will define that a certain path in the trellis must be traversed. And what we do is simply read out what is written off on top of each of the branches. The objective of the decoder again is to recover this particular path from the trellis diagram. So, here is in a nutshell all of it. If you see, this is the hardware followed by the mapping. So, I can describe my TCM scheme as a diagram with a circuit implementation and a mapping, or equivalently I can define my trellis using the states and a trellis diagram. They are the same, you give me one and I will give you the other. So, if you look at the path in the trellis, this slide tells me how to go from the input sequence to the path on the trellis, and the encoder takes 2 bits at a time and follows the consequent paths in the trellis and reads out the corresponding symbol written on top of that branch. So, this slide basically tells you that first branch has S5 written on it. So, read out S5, second branch has written S1 on it. So, read out S1, S3 and S3 and so on and so forth. So, now we go to the job of finding the free distance. We know that free distance is the single most important parameter which describes how good this trellis code is. So, the free Euclidean distance of the TCM scheme can be found by inspecting all possible pairs of path in the trellis, not just from the all 0 path. This is because we are dealing with a non-linear code. So, let us look at this diagram, and this is the same trellis coded modulation scheme described earlier. Here, after a lot of inspection, we have been able to identify one pair of path which leads to the minimum distance called the free distance. So, we have S0 S0 S2 and S7 S0 S1, they have been shown using bold lines, and clearly the distance is not coming from the all 0 path. In fact, the all 0 path does not lead to the calculation of d free here at all. So, if you add those free distances, so it is Euclidean distance. So, if you see, first we will take the distance between S0 and S7 plus between S0 and S0 plus distance between S2 and S1. But what distances are we adding? We are adding the Euclidean distances, and therefore, we take the squared Euclidean distance because we can add the squared Euclidean distance overall. So, we take the distance between S0 and S7, squared Euclidean distance, squared Euclidean distance between S0 and S0, and squared Euclidean distance between S2 and S1. If you add them up, you get answer equal to 1.172 ES. What is ES? Well, the radius of the circle is under root E of S. So, it can be seen that in this case the error event that results in the d free does not involve the all 0 path in the trellis, and we looked at all possible pairs in the trellis to find out d free, not just the all 0 path. Now, we have defined something called as coding gain. The difference between the values of the SNR for the coded and the uncoded schemes required to achieve the same error probability is called the coding gain. What is this gain? This G is SNR uncoded minus SNR coded. We had seen this definition earlier also. So, at high SNR, this asymptotic coding gain G infinity, where SNR tends to infinity, is defined as 10 log to the base 10 d free squared over E s of coded scheme versus d free squared over E s of uncoded scheme. This is called the asymptotic coding gain. So, for uncoded scheme, d free is simply the minimum Euclidean distance between the signal points. So, uncoded is in the denominator. So, let us look at the TCM scheme we considered earlier. We had calculated d free as 1.172 ES for our scheme, but for QPS the distance between any two signal points is 2 ES. So, G infinity is 10 log 1.17 divided by 2 equal to minus 2.3 dB, which means that we have actually lost out. The gain provided by the encoder, convolution encoder, did not more than enough compensate the loss because of movement to 8 PSK. So, we did not kind of win the game, we can do better, and that is what we have to look at. So, our performance is actually worse than the uncoded scheme. So, it is a two-edged sword, and it tells us that we have used the good properties of the encoder in terms of Hamming distance, but not the Euclidean distance. So, the aim of the design of good TCM scheme is to maximize the Euclidean distance. So, we did not do well in terms of TCM. So, we must now look at maximizing the Euclidean distance. So, how do we do that? Well, a proper choice of mapping scheme can improve the performance, and it is better to design the TCM scheme working from the trellis itself, because finally it is a d free that we have to maximize, and d free is calculated using the trellis. So, why not work with the trellis itself? So, the objective is to assign 8 symbols of the 8 PSK signal set in such a manner that d free is maximized. Okay. Now, in the last example there were 16 branches. because there were 4 states, 4 branches were coming out from each. So, there were 16 branches. We have to choose 8 symbols. So, how many ways we can do it for an exhaustive search? Well, 8 raised to power 16 different cases. That is just too large. Even a supercomputer, network supercomputer, distributed computing can't solve that. So, we need better heuristic methods to solve it. A computer search will not work. Why are we making this point? For convolution encoders, efficient computer searches had helped solve the problem, but not for this case. So, let us look at what is an error event. Well, error event we have seen when 2 paths diverge, they keep away from each other and then merge back in the trellis after some times. These red dots are the nodes in the trellis. So, we have just shown 2 paths which diverge and merge back. This constitutes an error event. And the one with the minimum distance between these 2 paths, distance in terms of Euclidean distance, comes out as the D free. So, at least what we can do, we can maximize the 2 branches where it diverges and merges back, and rest all will add to it, but we do not have much control how it jumps up and down in the trellis. So, we will choose the Euclidean distance associated with at least the diverging branches and the merging back branches to give us something. And we also know that there will not be too many hops. In 2-3 hops it combines back. So, it will not be a bad choice. So, we look at the diverging DE diverging path and remerging path, and we have a redundancy of 2 raised to the power m plus 1 memory signal set is used to transmit m bits. Why? Because we had this 8 PSK and then we went to from QPSK we went to 8 PSK. So, we have m over m plus 1 convolution encoder. In the last case we had 2 by 3, so m was 2. So, m shows that uncoded and m plus 1 is the coded. So, this is a typical case. You can have a 4 by 5, 7 by 8 convolution encoder. So, the resulting m plus 1 output bits are then mapped. So, we will use this concept to come up with some design methodology in terms of increasing the Euclidean distance. But the method to do so is called set partitioning, and let us discuss how it is done. So, the aim of set partitioning is to progressively increase the Euclidean distance and then use that partitioned set to map onto the trellis. Each time we partition the set, we reduce the number of signals points, but increase the distance between the signal points in the subset. Let us look at an example. Let us start with 8 PSK. On the top you can see 8 PSK, they are all placed on a circle. So, we now partition this is a set of 8 signal points, we partition it into 2, 4 and 4, but see the distance has increased. So, the minimum distance has gone up, but why should we stop here? We can partition it further. Again, there is more than one way to do the partitioning, but we partition it in such a way that the minimum distance in this partition set between 2 constellation points have gone up. So, here there were 8 points, now we have 4 points and 4 points highlighted by red, and then 2 points and 2 points, 2 points and 2 points. And then of course, you have single point in the sets. So, we have done the set partitioning of 8 PSK signal set. It is pretty mechanical, you can do it for any large constellation diagram. So, now the aim is how to use this partition set and map it to the trellis that we have here. So, what we do is we basically come up with a rule as to how to apply these points from the different levels of constellation diagram, because level decides what is the minimum distance in terms of the diverging and merging paths. Okay. So, again Consider the expanded 2 raised by m plus 1 signal set you use for TCM. We do not necessarily have to continue the process of partitioning till the last stage. Suppose the desired Euclidean distance to be obtained just after the m plus 1th set partitioning step is m tilde less than m. Then it can be seen that m tilde plus 1 steps we have got m tilde 2 raised by m tilde plus 1 subsets, each subset containing 2 raised by m minus m tilde signal points. So, as you go down, the number of signal points reduces, and you have to only go down to those many points for which you have the branches to assign to. So, you do not have to go right into the bottom of the pyramid. So, now let us look at a simple example of a general structure. Suppose you have got m bits. So, first you have a convolution encoder here. It is systematic. So, you have m minus m tilde points going directly to the signal mapping, and then m tilde over m tilde plus 1 convolution encoder giving you the coded bit streams. The first m minus m tilde points is used to select the signal from the subset, and these are used to select the subset. So, you have the subset, and within the subsets you have signals. So, this is a strategy how to choose the subset and then a particular signal from the subset, and this will give you a minimum D free in terms of the deltas. So, this is the general structure that we have just described, how you can use a TCM encoder. Now, we go on to Ungerboek's scheme, which tells us how to assign the symbols onto the trellis having done the set partitioning. So, the aim is to maximize the free Euclidean distance between coded sequences. So, just consider an example of a rate 2 by 3 convolution encoder, very simple 2 by 3 encoder, natural mapping we have shown below, and for that we are going to do an Ungerboek scheme, and here you can see that there are parallel paths in this case, because you know if this input A1 does not change, then the state transition does not change, and for A2 between 1 and 0 there are 2 possible outputs. So, there will be 2 paths from any one state to the next state, but the question is how to assign the symbols from the 8 PSK. So, here we have used the Ungerboek scheme, which we will discuss how to assign the different symbols from the. So, once you do a mapping as described earlier, then we can calculate directly the D free as the minimum of delta squared m tilde plus 1 and D free squared m tilde, which is E4, comes from the maximally separated points on the symbol set, and this tells you that the D free is larger than the uncoded one, giving us an asymptotic gain of 3 dB. So, we have been able to recover and we have been able to give you a 3 dB gain using a TCM scheme. This is called the Ungerboek's TCM scheme. So, let us look at the design rules first and then revisit the example. So, these were proposed in 1982 by Ungerboek. These are heuristic design rules. What are the rules? Well, they tell us how to assign symbols from the set partitioning to the trellis. So, if your trellis has parallel transitions, right, then they must be associated with the signals of the subset in the lowest layer of the set partitioning tree, that is they are maximally apart. Okay, they have the minimum Euclidean distance. Rule 2 is that the transition originating from or merging into one state must be associated with signals from the first step of the set partitioning. We already have done the set partitioning. And then rule number 3 is all signals are used with equal frequency in the trellis diagram. So, these are heuristic rules which will ensure good design of your trellis. So, we want to improve the trellis scheme we just proposed, and we want to improve the performance of that scheme using these design rules. So, let us look at a trellis with 8 states. Let us look at an example where we will execute all the points proposed by Ungerboek. So, this is a trellis with 8 states, and as you can see that there are 4 branches emanating from every node. Okay. So, there are 2 bits coming in for this convolution encoder. Okay. And there are clearly S0 to S7. So, there are 8 points in the constellation diagram. So, 3 bits are being mapped to the symbols. So, it is a RAID 2 by 3 encoder that has resulted in this trellis. Since there are 3 memory elements, therefore, there are 8 states in the trellis. So, the number of input bits is pretty much independent of the states in the trellis, which depends on the memory unit, and the number of output bits basically decide the constellation size that we will use. So, this is the trellis that we have at our disposal. So, there are no parallel transitions. We start directly with the Ungerboek second rule of assigning. So, in this trellis we have assigned S0, S4, S2 and S2 for these 4 branches which are diverging out. So, this is from the lowermost but one level of the set partitioning that we have done already. Similarly, we have taken the next one S1, S5, S3 and S7. These are the other 4 maximally separated points in the trellis, and so on and so forth, and we have made sure that these are assigned with equal frequencies. Okay. Same care has been taken for the diverging and the merging back paths. So, if you look at the points which are merging back, they have been also assigned with that same care. So, in this slide we are looking at the diverging path, and this slide describes why S0, S4, S2 and S6 symbol have been assigned to that. They belong to the subset A0. And for the next node we have done S1, S5, S3 and S7 as we just now discussed. Okay. So, we have done all of this, and the order has been shuffled to ensure that at the remerging end we still have the signals with the first step of the set partitioning. That is the care we have taken to do so, and we have also ensured that all the symbols have been used with equal frequency. So, we have been able to use Ungerboek's design rule to assign symbols to this trellis diagram with 8 states. Let us quickly calculate the D free. So, D free we had already highlighted the 2 paths which result in D free, and the D free calculation gives the G infinity to 3.6 dB. Therefore, this has an even better 0.6 dB gain over the TCM scheme discussed earlier by Ungerboek. So, let us now kind of conclude this lecture. What we have looked at is the notion of combined coding and modulation. Then we introduced the idea about trellis coded modulation and how we can get improved performance without additional power or bandwidth. Then we talked about the free distance and the Ungerboek's design rules. We also followed it up with some examples. With that, we come to the end of this lecture.